A very good morning to all who have joined in this webinar. We welcome you to this webinar on deep learning in mathematical perspective. We are happy to have you all here. We have certain instructions for the participants. Kindly disable your audio and video. Do not present your screen in between. Pin the speaker's presentation to view it without any disturbance. Feedback link will be posted in the chat box at the end of the session. If you have any queries, you can post in the chat box. It will be solved by the technical team. warm welcome to one and all present in this virtual platform on behalf of Department of Mathematics, St. Joseph Institute of Technology. We highly appreciate your efforts to join us for today's webinar, which we hope will be a fruitful experience for you. Inspiration does not seek for a destination, nor does it stop with a goal achieved. It is a continuum that drives people from one goal to the next goal. True to these words, our college management inspires us to move our goalpost further and farther to make meaningful initiatives continuously. Hence, I would like to express my profuse sense of thankfulness to our beloved chairman, Dr. Babu Manoharan sir, the managing director, Mrs. S. Jessipriya, our director, Mr. B. Sashishekar, and Dr. P. Ravichandran, the principal of St. Joseph Institute of Technology. We are privileged to have Dr. Kishore Kumar, P.K. amidst us to engage us and enlighten us on deep learning in mathematical perspective. Dr. Kishore Kumar, P.K. is a lecturer in Department of Information Technology, Mathematical Section, Al-Muzana College of Technology, Oman. He received his doctoral degree from Bharatiyar University, Coimbatore. His doctoral research was on graphs in uncertain environment. He is an esteemed specialist in fuzzy graphs, vague graphs, nutrosophic graph theory, Python programming, machine learning, and deep learning techniques. He has rich experience of 14 years in teaching mathematics in various reputed colleges in Oman and Chennai. Our speaker for today has been an exemplary student, and the list of proficiency praises he has received throughout his degree programs shows his passion towards mathematics. Dr. Kishore Kumar has numerous publications in reputed scholarly journals and has presented various papers in conferences too. His contribution of chapters to books like Advanced Engineering Research and Application and Nutrosophic Operational Research is noteworthy. Thank you, sir, for kindly accepting our invitation to be a resource person for the session. It is a pleasure to have such an academician with us for this webinar. I have certain instruction for the participants. Kindly disable your audio and video. I request to unmute your audio and disable your video. We find certain participants have not disabled your video, so kindly disable your video. And do not present your screen in between. Pin the speaker's presentation to view it without any disturbances. Questions to the speaker can be posted in the chat box. It will be taken to the speaker at the question and answer session at the end. Feedback link will be available in the chat box at the end of the session. So do not ask for feedback in between the session. Once again, our esteemed speaker and dear participants, let me extend my hearty welcome to you all once again for this webinar. Over to the speaker. Hello, sir.
Good morning, ma'am.
Good morning, sir. Thank
you. Can
you
you hear me?
Yes, sir. Yes, sir.
Thank you for a nice introduction, madam.
Yes,
Thank
sir,
you.
Yes,
good morning, all. Eid wishes to everybody. So I'm Dr. Kishore from Musana College of Technology, Oman. First of all, I'd like to thank the management for giving me this wonderful opportunity to present over here, and also my colleagues and friends who are with me. And I'd like to thank the conveners and the coordinators of this program who has taken such a wonderful effort in this pandemic to conduct such a wonderful program. I hope you can see my screen, right? Are you able to see my screen?
Yes, sir.
Fine. Yeah. So in today's webinar, we are going to see some of the concepts on deep learning in mathematical perspective. So we are just going to have a prelude on what is deep learning before getting into mathematical perspective, and we are going to see some of the rudimentary concepts in that, and also we are going to see how an algorithm works with a mathematical way of behavior and how the learning occurs in an algorithm. So all such things we are going to share today. And before getting to deep learning, I just quickly have a review on what is data science and about what are the components behind data science. So we will see. All right. So this slide shows the fundamentals of the foundations of data engineering. So there are three main components behind this. One is artificial intelligence, the other one is machine learning, and the third one is deep learning. So I'll just talk about that. So what is artificial intelligence? It has been evolved in the year 1950. AI is the effort to automate intellectual tasks normally performed by humans. It is a general field that encompasses machine learning and deep learning. For example, chess programs, on those days, it has been hard coded by the programmers by their own rules. But later on, it got automated by the machines, and henceforth, the artificial intelligence came into existence. Right. So we'll just see about it. Then comes machine learning. It is found in the year 1843 by Ada Lovelace, who is a friend of Charles Babbage. And recently it has been developed in 1950 by Turing in his works in Turing machines. So it is just to talk about, could a computer go beyond what we know how to order it and learn on its own to perform a specified task, or a computer just automatically by its own by giving set of rules and looking onto the data to perform it. So in classical programming, the human gives the input, the rules and the data to be processed, and we are getting the output. Whereas in machine learning, human inputs the data and answers to data. That means the answers are also known to the computer, and based on that answers, it gets trained and it produces some rules by giving the new test data. So that is going to be the outcome in machine learning, right? So here is the structure we have in traditional programming. We have the rules and data, which is going to be inserted as an input, and the final output should be the answers, which is going to be produced by the machine. Whereas in machine learning, the answers are already produced before, and you're going to get the set of rules or the functions which is going to predict the outputs for the real-time data. So this is the new programming paradigm we have. So what are the tasks of machine learning here is, it inputs data, for example, like speech recognition, sound files, image tagging, the pictures we tag in. So we are all very familiar with Facebook and all those things, tagging the pictures and all. So what it does is like, it is just producing the output, like human generated transcripts in case of sound files, or image recognition of the pictures. For example, the picture you're going to tag in will represent you, who is your friend, like that. So you can just use the machine to identify that. So that is the expected output. And the way to measure is by the algorithm here. So we're going to go do some of the job with the algorithm. Like we are going to measure the predicted output with the original output, and how far the algorithm is working efficiently. That is how we work on. All right. So a classical example of machine learning is, let us consider some points which is going to get plotted in XY axis. And we have some points, some white and black points. Now we are going to develop an algorithm which could predict these points and which could classify these black and white points. Okay, we are just going to fit these coordinates in a plane. I'm sorry, in a one-dimensional plot here. You can see this picture. So this picture represents some of the black points and the white points here. The inputs are the coordinates of 4 points, and the expected outputs are the colors of 4 points. Okay. So now we're going to categorize, we're going to classify these points, okay, by segmenting it. Okay. So measuring the performance of the algorithm, it is based on the percentage of points that are going to be classified correctly. Okay. So in olden days, what a human being does is like, he just collected the raw data and he is just making the coordinate change by hands. Okay. He just transform the coordinates in, this X and Y axis tilted in this way. And finally, he got a better representation where the points which are lesser than 0 in the x-axis gives the white color, and the points which are greater than 0 in the x-axis gives a black color. Okay, so you can just classify in this way. This is the usual way of classifying, okay, by human being. But how does a machine going to do this task? Okay, that is our task here. That is our understanding. So the output in this example deals with the human-made coordinate change. Learning in the context of machine learning describes an automatic search process for better representations, and all machine learning algorithms consist of automatically finding such transformations that turn data into more useful representation of a given. So whatever I said before was given in this lines in this slide. All right. So now we will just get into deep learning. So this is what a machine learning does actually, right? So there are a lot of algorithms in machine learning also, which is giving an efficient output for a set of data which we are inserting, okay, with a trained data set. All right. So now we'll get into deep learning. So we'll just understand what is deep learning. Deep learning is a specific subfield of machine learning, actually. So it represents the data that emphasizes on learning successive layers of increasingly meaningful presentations. So here, the word deep in deep learning stands for the ideas of successive layers of representation. So what is the difference between machine learning and deep learning is, in deep learning, we have certain layers between the input and output, okay, where that layers tries to filter and try to give the output, okay. So we're going to get the output in a better way so that, the machines acts like a human being there, okay. So the number of layers contribute to any model is termed as the depth of the model, actually. So how many layers are there in between input and output, they are called as the depth of the model here. Fine. So now deep learning has achieved many things in recent days, like it is near human levels image classification, it comes across speech recognition, then handwriting transcription recognition, then machine translation, then text to speech translation, which is using some digital assistants like Amazon Alexa, and human level autonomous driving. You have seen some driverless cars, right? So like that, and you have some search on the web pages, okay, results on the web, improved results on the web, and ability to answer natural language questions, and improved ad targeting used by Google, Bing, and Baidu, and by superhuman Go playing. Like you can even play games based on the motion capture. Okay, all these things have been done by deep learning nowadays. So deep learning has just taken over machine learning with a lot of its, human intervention between with the layers which has got. So deep learning assists humans in science and software development and much more. Okay, so this is the picture which is clearly showing us the outer layer, which is the artificial intelligence, and the middle layer, which is having the machine learning, and inside you have the deep learning. So you can see artificial intelligence is a system which is going to have, the smartest system which is having, which works without human intervention. And machine learning and deep learning are the applications of artificial intelligence here. And of course, deep learning has captured it has got its own significance compared to machine learning, and henceforth it is taking the place from machine learning, right? All right, so we'll get into deep learning today. I'm not going to talk much about machine learning. I'm going to talk about deep learning today. So with the basic understandings of deep learning, what it is, we will try to figure out some of the important tasks here. So one of the basic and very important concept in deep learning is the neural networks, which plays a vital role in connecting the input and the output here. So the layered representations are almost learned via models called neural networks. Okay, so we have a set of input, and it is going to produce the output. In between, there are some connections. Those connections we call as a neural network. So of course, it is just trying to simulate the functionalities of the brain here, where a human brain thinks. Okay, and the neural networks refers to the neurobiology drawing, the basic functionality of the brain. But still, deep learning models are not models of the brain. Of course, it is just trying to simulate the models, not exactly what a brain does. Fine. And it is a mathematical framework for learning representation from data. Okay, so whenever we come across this word neural networks, it of course have the behind the screen mathematical analysis is there between the concepts which are dealt in deep learning. We will try to understand what it is in the forthcoming slides. Okay, right. So now I'll just show you a figure where it is trying to take the original input, the handwritten number 4, and trying to give the output as identify the output as 4 here. How does it work is there are a lot of layers between. So here I'm they have connected roughly with 4 layers, okay? And each layers have its own significance to capture this image, okay? Because this image has been classified into a lot of pixels, and these pixels can be captured in each layers, okay? So that each layers learns by itself and trying to come out with a better result, and finally it is leaving out the result as 4 here, okay? The final output is 4. And what is this layer? What does it do? All these things are clearly explained here. You can see how the image has been captured first, and it is learning by the algorithm which we are going to create actually, which we're going to use for the particular task, and it just captures it, and finally it's trying to come out with the output. Okay, it is just trying to capture the grayscale areas and black and white pixels here, and trying to find the output as 4 here. Okay, so that is how it works. Okay, deep learning representation learned by a digital classification model. So I think this can give you an understanding of what is deep learning exactly does. Okay, whereas a machine learning doesn't have this kind of things. It directly moves with an algorithm and gives the output, whereas deep learning has got a lot of filters between, or the layers between, even maybe hundreds of layers between to get the exact output, which is exactly acting like a human being did. Right. So now to get into the technique, we have we were just seeing what is our neural network here. Now we're going to see some of these concepts in this picture. You can see this layers what we had here. Okay, these are the layers we have. For example, I'm taking two layers here, and these two layers are connected with the weights. Okay, we have certain weights. Okay, to read that, I mean to understand what does it do exactly. So each layers are related to some weights. Okay, and these weights, and we call it as W here, and we have some the inputs we call it as X, and when we multiply we get W into X, actually like that it works, and we just sum it up, okay, all these things, and we are going to predict some results. Okay, so the prediction here we are going to see is this Y dash. Okay, so this Y dash is going to be the predictor output for the data which is going to be passed inside the machine, right? So this is neural networks which is parameterized by the weights. Okay, now not only that, after prediction, it has to compare that with the true targets, actually the true values of that x-axis. Because if you want to give some data with the answers, actually, now the machine is going to perform with an algorithm, and which is going to give you the prediction here, and that prediction should be measured with the original target. Okay, you have got the set of data which is the answers here. Now we're going to compare that with the predictions here, right? So when you want to just compare these two, okay, we want to check the measure between these predictions, okay, the predicted result and the original result. We have to see how far it is very close to the original one, okay, the predicted result. So to compute that, we have something called loss function here, which is going to use the loss score, okay, so which gives you the output, like I mean, based on the loss score. Whenever the loss score is minimal here, okay, then the prediction and the true outputs are going to be very closer. Okay, so how does it work out here? You can see here. So this is the performance of the machine. Okay, I mean the deep neural network, and finally it is producing the output Y dash, and it is just comparing with the original true target, and you're getting a loss function, and that loss function computes the loss score. Whenever the loss score is more, then there is no efficiency by the done by the algorithm. Then we have to optimize that. That means we have to minimize the loss score. Our aim is to minimize the loss score, whereas the weights get updated between. Okay, so whenever we come across this situation in neural networks, we call that as back propagation. So this back propagation is something like we need to go back and try to update the weights here. So whenever we try to update the weights, so that again we'll try to compute the predictions, and based on the predictions we have to compare with the original results and try to get the loss score, and we try to get this loss score getting minimized here. Okay, so when the loss score is getting minimized, then we can say that the the algorithm is working fine. One second. Right. Am I audible?
Yes, sir. Audible, sir.
Am I audible? Yes. Yeah. Fine. So I'll move on to the next slide. Thank you. Right. Now, to work on this deep learning, we have some of the software packages built over the top of Python programming. We have Python 3.6.8 is the latest version we have. Of course, it is upgraded to 4 also. And you have something called Keras, which is the high-level application interface, which is having some of the components or the packages behind it. These are called work engines. We have TNO, TensorFlow, and CNTK, which are some of the work engines which are going to be used with Keras. So this is one set of package which can be used to work on deep learning. The other set of packages which has come out with something called PyTorch, which is going to use the lower level API, and it uses the array expressions or the NumPy rules to work on this program. All right. So now we have, whenever we want to perform this deep learning, because we want to train a lot of data with images, sound files, video files, and etc., it will definitely capture a lot of spaces in the system. Like we can't do it very easily. So we should have a very good system for that. Of course, a system should be built with a graphical processing unit rather than going for the central processing unit. So to load the data and perform, we need to understand it will take a lot of space in the system. So the system should be having the performance with high level to work on this package. All right. So this is the software side of this package. So anyone who wants to learn these packages, they can directly learn and directly get the predictions and everything by online code. A computer scientist can do this. But as a mathematician, how do you want to understand? That is our task today. Okay, it is something like it is like a car which anybody can drive, but we need to understand the mechanism of the car, how it works or how it performs. So we need to understand the mechanism. That is the mathematical concept behind this deep learning, which we are going to learn today. All right. So we'll just try to go with some basic neurons which has been built. This is the foundation of artificial neurons. We have something called MP neuron and perceptron. Let us try to understand what is MP neuron. So MP neuron, we call it as Macaulay Pitts neuron. It is developed in the year 1943 by two persons, Macaulay, who is a neuroscientist, and Pitts, a logician here. So this is how a brain works actually. A brain has got something called soma here, which is a big channel, and we have something called dendrites, and it is connected through a cable which is called axon, and we have the synapse. Okay, so whenever we are listening or hearing something, how do we react? It all occurs based on this network, okay, which is in the human brain. So based on the same principle, the machine can also do some work. So they have founded that basic artificial neuron, which is called the MP neuron. So the MP neuron has got a lot of inputs here. These inputs are binary coded. We have the inputs from 0 to 1, and you have the function G, which captures all the input and it just adds all the input, okay. And then based on that aggregation, we are going to take another function F, and we are going to fit that into that function, and we're going to produce the output, which is going to be 1 if this g of x is greater than or equal to theta. Here theta is nothing but the threshold value we're going to set for it. So whenever the threshold value, if the output is going to be greater than equal to 0, then it is producing 1. If it is going to be less than 0, it is going to produce as 0. Okay, so based on certain decisions which has been done by F over G, then we will be getting the output here. Okay, this is a basic idea of analyzing the neural network model, okay, which is the preliminary one, MP neuron model. So this is the starting level. Then this works with the binary data. You have zeros and ones as the input, and the output produced is also having zeros and ones. Usually it is used in the classification model. Whenever we want to classify, we will classify it as yes or no. For yes, we are going to give 1, and for no, we are going to give 0. So this is how we classify. Okay, so for classification model, this is going to give you to some extent a good efficient result. And this is working only for the linear models. That means linear equations with a line we can classify it. Like how do I say? We just classified the black and white points. Hope you remember the previous slide, right? Like that, we are going to classify it here. Okay, it is a harsh line we have in the graph. All right. So now we're going to move in the perceptron model, the next model, which is called perceptron model, which has been found by Frank Rosenblatt in the year 1958. What he says is like, again, with this inputs, we are going to give some measures, okay, for each and every input, okay. That means some learning rate, okay, how about that input, the information is passed, okay. There are some weights. Now we are going to just combine this weights with the inputs, okay, and we're going to give it to the machine here, okay, which is having two functions G and F. Of course, G is going to aggregate everything. We're going to multiply all these things and sum it up, okay. That is what happened here, sum of Wi into Xi. And we are going to have a threshold value B here. So based on this threshold value, we're going to just classify whether it's going to give you 1 or 0. Okay. How does it work? It is just going to fit into this function F. F is going to take this G, and based on this G, it is going to give a decision whether it is going to be yes or no. Suppose if I'm going for a play out today, I'm going for a match, whether I can go or not. Based on certain seasonal conditions, I can work on that, and I can, based on some threshold value, then I can measure these things, whether I can go or not. I mean, yes or no, or 0 or 1 or 0 here. Okay, so that is the output. So these are all some classification techniques. You can see this picture, which is going to classify this red and blue points based on a line here. Okay, so everything we're going to fit in here is based on the linear equation, or a linear, linear equation obviously is going to give you or produce a linear, I mean a straight line which has got a fixed slope here. Okay, so that is how we classify. All right, so now this is the basic understanding of perceptron model. So these are the two models which has been evolved in the olden days. Like people have found this artificial neurons, but what is the drawback of this model is like it does not have a smooth curve which can cover. For example, if you have a large number of points like this, for example, here you take the salary in some dollars, okay, $1,000, like 11,000, and the family size here. And the predictor output, the output here is like to buy the cars or not based on the family size and the salary a person gets, whether he is going to get the car, purchase a car or not. Purchase a car means 1, if not, it's 0. Okay, that is the output here. So how do we plot that? Okay, you have seen here there are 2 inputs, x1 and x2. We can say for salary and family size. So we're just plotting it inside with this colors. Red indicates zeros here, and 1 indicates green indicates ones. I just show only few elements here. Okay, there are a lot of values. Okay, if you see a lot of points here, because I mean I can't show it here, so I just showed in this picture. You have a lot of points here, which is plotted here. Fine. Now here, if I go for this perceptron model or the neuron MP neuron model, then I can just draw a line between this. Okay, and I can segment it, but it will not give you an efficient way of classifying this points, because some of the points are when you draw a line. For example, you can see this picture. When you based on some weights, okay, we pass. Okay, we draw a line here. So here, there are 2 regions here. In this region, you can see some green points. In this region, you can see some red points. Okay, and also how do we classify this? This is being classified from 0 to 1 here. Okay, so 0 means the person is not buying the car. 1 means the person is going to buy the car. So in this region also there are some red points. Here also there are some green points. And you can see in this boundary whether the person who is having a salary of 10K, he can jump into this region or that region. Okay, it depends on his, he's in the fence. So it is very hard to classify based on this linear line. Okay, it's very hard, of course. So based on this situation, we need to understand. And of course, you can see this, 2.5, and he's having, it is showing here. Okay, the top place, which is 1 here, and this point is -1, which is at the top. Okay, that means the person can buy a car. So these are the the original output, and if you're going to measure it with the predictor output, then how efficient it works on, we need to plot it. Understand? So this is how we are going to work on. Right. Fine. Now we have a picture here which is going to show you the new model, which is called a sigmoid neuron. Okay, so what is a sigmoid neuron does? I will come back to this picture. Before getting to that picture, we will try to understand what is called a sigmoid neuron. Okay, a sigmoid neuron is a neuron which is having an S-shaped curve like this. Okay, now we are going to smooth this curve. Okay, we have got a lot of slopes in this curve. The slope is not fixed here, and we have got a threshold value 0.5 here. Okay, so based on this threshold value, we can just set the points, and we can just try to fit this curve, the sigmoid curve, with the original true or the targeted output here. Okay, so that is how we're going to do. So here this data has been having the real inputs. Okay, it's not only has zeros and 1, it has also got some real inputs like 0 point something between 0 and 1 also. Okay, so all the inputs are taken, and it is going to get normalized to 0 to 1. Of course, it is going to get binary coded. Okay, and we call it as one-not encoder in Python programming to make it zeros and ones. Okay, and then the task is here we can go for 2 things. One, we can go for classification. The other one, we can also go for regression here. Okay, so here what is classification is? Classification shows something like to categorize these points. Okay, this is called classification, yes or no, like that. Okay, but whereas in a regression, we are going to find a value by using a regressor. Okay, we are going to find a value. For example, you're going to find the probability value where the percentage of chance that a person goes out, or the percentage of chance a person buys a car. So these are all the properties of regression here. Okay, so the sigmoid neuron works with both this classification as well as regression. That is the task we're going to do it here. All right, and the model which we're going to use will be a smooth curve, which is going to be very smooth at the boundaries, and also the equation which we are going to represent, it's a non-linear equation where we are going to use with this sigmoid neuron. Okay, so this is the equation. We call it as logistic function, which is going to be used in sigmoid neuron. So that this equation is not linear, it's non-linear. As you know, as a mathematician, you can understand what is a non-linear system, and any non-linear function can be represented using sigmoid neuron. All right, so now, so to compute that, we are also interested in to learn about loss function, which is a very, very important step. So here we call something called as square error loss function. Okay, we are going to take the original output, and we're going to take the predictor output. We are going to find the difference between that, and we're going to find the square of that, and we're going to sum it up. Okay, so this is the basic idea of square error loss function. And you have a lot of other things, loss function, something like mean square error. Okay, we're going to take the average of this, and of course we can take the root mean square error, which is nothing but we're going to take the root of this and we're going to find the answer. Okay, that is root mean square. And of course we have another square, another loss function, which is also called as cross entropy loss function, which is going to have the higher level concept like information content and probability to measure the loss function. Okay, so that is a kind of loss function which we are going to use in software packages, of course. Now we are basically interested in to learn about the square error loss function here, right? And the learning algorithm is more generic learning algorithm which we're going to use, okay, to understand the iterations, okay, based on this passes of the epochs, and we're going to fine tune it to get the loss getting minimized here. All right. And the evaluation process, of course, we're going to find the accuracy, where the accuracy is measured by out of total number of predictions, how many predictions are going to be correct. Okay. So we're going to find the true positive output for this function. Okay. All right. So now here, as I told you, we can't classify it with a harsh line. The line is very harsh, so we can't classify. Whereas with the two inputs, we can draw a sigmoid curve. A sigmoid curve will be it is a two-dimensional figure where you can see here x1, this side is x2, okay, and this is the loss. Sorry, this is the function which is having from 0 to 1. We are measuring it up, okay. You know, for 0 means it is no, and 1 means it is yes, right? That is the classifier, okay. All right. So now we are gonna just see this two-dimensional figure here. It is a plane, of course, you know. This plane, when you view it from the top, you just think you're just viewing from the top like a plane. You can see this plane. So this the red color which indicates 0 here, and when it goes up and it is finally touching 1. All right. So from 0, it is going to go with 1, of course, right? So now you just draw some lines and you view from the top. So it is getting segmented here. So you can just have a better interpretation with the sigmoid function. Okay, this is a perceptron model with sigmoid decision surface, where you can see here this red line indicates some points which are zeros, and slowly when you move on to the orange colors and these colors, you can see this is having some 35% of the chance like a person can buy a car, and these are giving some probability values which is going to give you some input. Okay, so based on that probabilistic approach we can deal with. Still, it is not going to give you the exact decision, okay, but we can compute by using sigmoid neuron decision boundary a better interpretation rather than comparing with a harsh line in perceptron model. We can put it into the sigmoid neuron and try to just view it in a probabilistic approach. These are the probability values where you can see some 15% of a red region is showing like they are not going to buy, then orange is showing you some percent of chances they are going to buy, okay, like 10-20%, and finally this green is going to show this many persons are going to buy the car surely, okay, like 1% is there, like that you can understand. So this is the way to interpret. All right, so based on this it works actually. Now I'll just move on to the mathematical understanding of the sigmoid neuron. So we're going to compute the mathematical understanding of a sigmoid neuron, right? So we will just do it now. So I have another slide. Okay, I'll just show you that. Okay, this is the other slide, which is going to give you the mathematical concepts on a deep learning algorithm. Here, I just took this sigmoid neuron and I'm trying to show you what are how the loss function is computed and how it uses the mathematical concepts behind. So you can see this picture. This is a sigmoid function, or the smooth S-shaped curve, okay, which can better fit into all the data values, values of the data set. So can we have a smoother function in a classification problem? So yes, of course we can do that. And the sigmoid function provides a smoother S-shaped curve as opposed to a step line function. Okay, so based on the learning grade here, we can just try to fit this curve exactly to the original output. Okay, that is what they are telling about. And the sigmoid function is given by 1 by 1 plus e power minus summation wxi plus b. So this is the function we have. So this wi and xa are nothing but some scalars which has been multiplied together. Okay, so we have to take the transpose of it and we do it. So that is the way we can take, because we multiply this, one has to be in the row, the other one has to be in the column, so that you can multiply and you can add with the bias. So this bias is nothing but the kind of slope which you're gonna have at any point. Okay, we're gonna the slopes are getting varied here. So based on a lot of variations, you're getting the family of sigmoid functions, of course. Okay, because it's not only one function. I mean, based on the values of w and b, you're getting a lot of sigmoid functions, and one such sigmoid function can be fit into the original output. We will try to view it, of course. Okay, so I just show you the basic understanding of that. Okay, fine. So now this is a figure which is showing the two-dimensional plot, like you have a a two-dimensional figure with the two inputs x1 and x2, and this is from 0 to 1 how it is going to be viewed. Okay, as a two-dimensional with the two inputs. Okay, fine. With the two inputs, we say we have x1 and x2, which is having two weights w1 and w2, which are multiplied, and we're going to get that gets added together, and you're going to get this function. Okay, so this is how you're going to get the sigmoid function. Okay, so we're going to substitute this w and x values to get the two-dimensional form. And when this w and x, when the power of the exponential function which we have, it's going to be, if it is vanishing or if it is 0, then we'll have e power 0, which is 1, and 1 by 2 will be 0.5. That is the output we get. And this 0.5 is nothing but the threshold value we have for this. Okay, for this, I mean, this is the output. Okay, we have 0.5 as the threshold value. So based on that threshold value, we can just classify, of course. Okay, that is how we are working. All right. So now we have this sigmoid has got two loss functions. The basic loss function is the squared error loss function. Okay, or the square loss function. So this is the basic one. Of course, we can take the average of that to for some circumstances. And of course, we can use the root mean square also. So recently, they're using the average method to perform in the packages like PyTorch or TNO or TensorFlow. Okay, so but we have another set of entropy function which is called as cross entropy function, which is also a very good loss function, which is able to predict the exact loss. This is also used in the package, okay, Python package. All right. So now you have, we just want to see how this loss function is computed. You can see a small example here. You have two inputs, x1 and x2, right? And you're going to, you have some output here, y. Now we're going to predict some output, okay, which is called the predicted output, which is having the notation y hat. Okay, this y hat is the predicted output. Okay, now we're going to compare this output with predicted output with the original output here. Okay, this y, and we're going to find the difference, and we're going to square it up, and we're going to sum it up. Okay, the sum of the difference of these squares will give you this output. Okay, this is the loss function. This is how calculated. If I'm correct, I hope this answer is right. Okay, you can just verify it is right. Fine. Great. Now, in sigmoid neuron, each individual points contribute differently to the overall loss. Now, what this exactly mean is like you can see here, these are the output. Y is the output. Okay. Here we got original output 0.5. Now, the machine is doing this work, okay, with the input x1, x2, and is going to predict y hat. Okay. So y hat is the predictor output by the machine. This is the original output. Now you see the difference here. It is 0.5, 0.6. Little subtle difference, right? And you have this 0.8 and 0.7, very, very little difference. Here it is same, but here you can see a large difference, 0.4. So this, each individual points contribute differently to the overall indicates this predictor output results, which is having a far distance from the original output. Okay, that is how we are trying to interpret the loss functions. So based on these points, which we're going to get as a predictor output, we are going to define the loss function. Okay, that is the way to understand. All right. So now the learning algorithm, what it does exactly, we are going to make the curve smoothened here. Okay, this curve. Okay, how far we're going to smooth it and how far we're going to fit it. We are going to use something called as a gradient descent method here. So what the learning objective of that is, in sigmoid neuron or any other model, the parameters that influence the way the output is predicted is something like the curve is going to get plotted in that graph, okay, with a smooth boundaries. All right. And we are going to change these parameters. Based on the parameters, the curve also gets changed. Okay, and the output of this will definitely learn from the training data and trying to minimize the loss also, of course, to get into the model fit here. Okay, so these are more theoretical, of course, maybe somewhat dry, but still I will try to make you understand with some figure. Okay, we are going to do that. So what are the steps involved in sigmoid neuron is we are going to initialize W and B. Already, as we said, what is this W and B? We will just is W and B or nothing but the random initialization. That means we have the weights as well as the bias for them. Okay, So that is how the sigma neuron uses these things. And we are going to iterate over the data, okay, the original data, and we are going to constantly keep updating this W and B for each iteration, okay. We are going to update this W and B so that we are going to find the loss function for this, okay. And based on that loss function, we are going to decide whether this algorithm is working efficiently. Suppose if the loss function is more, we are trying to make it minimize. So our objective is to optimize. That means we are going to minimize the W and B, okay, minimize W and B so that the loss function is going to get minimized. That is the mathematical model behind this sigma neuron function, okay. We are going to do that. So how to learn this? See, this is by learning by guessing. For example, you can see here in this, okay, there are some input and output here. So this output are the original output we have, okay, 0.268 for 3, 0.73 for 4, 0.952 for 5, 0.999 for 8, okay. There are some input and output, okay, the data set has got, this is the original one. Now, we are going to use this W and B, okay. Based on this W and B, we are going to find the new predicted output, and based on the predicted output, we are going to find the loss, okay. And whenever the loss is going to get minimized, this algorithm is going to work efficiently. That is what we're going to find here. So what it does is, this is by we are going to learn by guessing, but this is not an efficient way to learn, of course. But still, we can, as a human being, we can do in this way. Like we can take the initialization of the parameter W and B to be 0. Initially, if we just fix as 0, and we are going to iterate over the data. That means we are going to guess and update this Xi. What does it mean is like we are going to change this W with a small parameter, okay, which is called as delta W. It's a small difference, okay. So we just increment this W with small increments here, okay, which is the negligible difference, which is called as W plus delta W, as well as the bias gets incremented with B plus delta B. When you increment both for this increment, okay, the new W plus delta W and B plus delta B, the new amounts which are going to added with this W, what is the guess? How far the algorithm is going to efficiently fit this model? We are going to compute the loss for this, okay. Now, once you try to find this, I will tell you in a better way to you can just view a picture and you will try to understand what it is actually, okay. So as of now, it is more theoretical and it's an algorithm, so we need to be very patient to understand this, of course. So you have this delta W and delta B. These are the amounts we changed W and B by guesswork, okay. We're going to guess this. We are not going to find it using the principal way of finding using some algorithm. We are just going to, as a human being, we're going to guess some numbers. We are going to add with this 0, and we are going to get a new W and B. Based on that, we are going to work out and we are going to find the loss function. And we are going to compute this, okay. So until we are going to get satisfied with the loss function minimality, okay. Once the loss function gets minimized, we are going to stop this process. So there are, okay, I will just talk about that. Now you can see, manually change the slope W and the midpoint B till it looks to fit the data, then perform a fine tune to match the training set as closely as possible. So what is the meaning of that? I will tell you now, okay, in a moment. So we guess the weights and bias by trial and error method, and we are just finding the W and B here. So this computation is going to happen, and for this W2 and B minus 7, we are going to have a sigmoid curve which is exactly going to fit the training data set, okay. We're going to fit this curve into the training data set. That is how it works on. So this W equal to 2 and B equal to minus 7 is a random guess, okay. So we have to compute by our own calculation, and for this W and this B, we are going to fit this curve, okay. That is what we are interested in. Fine. Now this is only possible in lower dimensions like one input or two inputs, okay, maybe one dimension, two dimension. Going beyond the level of more inputs, then it is very complicated to find this weights as well as the bias. A human being cannot do, okay. So for that reason, we are going to develop the algorithm which does it automatically. Of course, in PyTorch, we have a one-line command to find this W and B, okay, by giving the loss function, okay, by checking the loss function, whether it is maximum, it is trying to get reduced by using this different W's and B's, which the machine is going to give you, okay. It's a one-line command which is used in PyTorch, right? So we will directly use that, okay. But as a mathematician, how it is going to work, how this learning algorithm is going to work, we are interested in finding out that, okay, today, right? So now this picture shows this. I told about this, this points, right? So there are 4 points, okay. So of course, 1 point is I have removed actually. There are 2 is also there. So this 5 points have been fit here. Okay, this is the original data. Okay, now this blue line is nothing but the sigmoid curve, which is going to fit this, this points. How do it gets fit in this point is based on the values of the weight and the bias. Okay, W equal to 2 and B equal to -7. How do you compute this 2 and -7 is exactly like we need to work on different weights and different bias. Okay, I will show you the computation, how we are getting arriving at this. So we are going to work with different values of W's and B's, and we are going to find the loss. And the loss, we are going to check whether it is going to be decremented, because our aim is to decrease the loss from higher level to lower level. Okay, so we are interested in minimizing the loss. So whenever the W's and B's are changed, we are going to check the loss, and whenever the loss is getting decreased, maybe the loss may be leading to 0 also sometimes. Okay, the answer may be the loss answer should be sometimes it may be 0 also, so that it gets exactly fit like this. Okay, here in our computation for W equal to 2 and B equal to -7, the loss function is the loss value is 0, where the sigmoid curve is exactly fitting this the original points. Okay, the data set here. Fine. So this is how it gets fluctuated for different points for W's and B's. Okay, you can see this picture here. Can we connect this to the loss function? Of course, we can connect it. So you can see we are going to iterate this W and B, okay, until we reach a minimal loss, okay, for the training data set. So this is by using a smooth descent method from the initial value to the minimum. The loss fluctuates each iteration. For example, you see iteration 1, we have started with 0 and 1, and I'm interested in finding a loss function. How to find a loss function? I was telling you just before. We are having the original output and the predicted output. We are going to find the difference, and we are going to sum it up, and we are going to find the average of that to get this answer. Okay, so you can very well use an Excel sheet or a Python program to compute this directly. It's a very simple task, right? So you got this answer. So in the next iteration, you are interested to increment this W as 1, whereas the B value is 0. So for this 1 and 0, the loss function is computed 0.1064. Now you see the previous loss and this loss, it has got this new loss is going to be lesser than the old loss. Therefore, the output is decreasing. So of course, the loss is decreasing here. For this, for another random check, for example, you take W get incremented with 1 more, it is 2, and the B value is still 0. Further, the loss is 0.1210. It is getting increased. Why? Because you have the new loss is going to be greater than the old loss. So it fluctuates. The loss fluctuates here, of course, increasing, decreasing like that. So we are interested in finding with a different set of values. So this one we are just randomly checking. So based on these values, our loss function is getting fluctuated. And finally, at one set of values, you have W to be 2 and B to be negative of 7, -7. So you have this point. For this point, you're getting the loss function as 0. Okay. So this loss function is 0. That means it is definitely lesser than the previous loss, because it is arrived at the minimal level, which is 0. Therefore, the final decrease here is dealt. I mean, we have arrived at the loss function to be null here. Okay. So this is one case. So not all the data set will match this. For some data set, we will go on have this pass. These, or we call it as the iterations, we call it as passes here. We may compute it to 1,000 passes, 10,000 passes also. It depends on, we call that as epochs here. Okay. So it depends on the iterations, how far the loss function can be computed. Sometimes the loss function may be 0. Sometimes the loss function may be very, very minimal, so that like some epsilon, okay, which is very minimal, so that we can stop the process. Or sometimes we have to stop the process for 100 passes or 100 iterations here, and still that is going to be efficient for some data set. So that is how, based on the loss function, we are going to fit this sigmoid neuron. Okay, this is only one input, okay, and one output, what we call, okay, single input, single output. Okay, just X and WX plus B. That is the way to understand. Fine. So for that, we found this loss function. All right. Now, this loss function I'm going to take this W and B. I'm going to fit this as a 2-dimension. Now this 2, I'm going to pass it as an input, and I'm interested to compute this loss function, how it gets decremented. I'm going to show it as in the figure. You can see this picture. So this erratic fluctuation is undesirable. We can't say whether this fluctuation is increasing, decreasing or all, but still we can try to understand this algorithm, how it works and how it gets the decrease in the loss at every iteration. Here you can the following figure shows the loss plot. This is the loss plot based on the weight and the bias. Okay, W and B. Now the lowest point, which is going to refer to the minimal loss, which corresponds to the parameters w equal to 2 and b equal to -7 respectively. You can see here, this is your w, okay, and this is your b. We're going to fit it in this, okay. How to fit this based on the loss, okay. The loss is from 0 to, it goes, okay, up to 1. So you can see here, but what is our interest? We are going to just decrease the loss, okay. We are going to minimize the loss to 0. So you can see here, at this point, w equal to 2, I'm sorry, at this point, you can see this hands here, hand icon. At this point, w equal to 2, and at this point in b -7 here, somewhere, here you can see this point to be minimum, okay. So it reaches to the minimum. This is 0, the loss function is 0. So this is the loss curve in 2 dimension, where the loss is very high, okay, and it is getting decremented and somehow it flattens up, okay. But still, at which point is getting decremented? At the point w equal to 2 and at the point b equal to -7 here, okay. At this place, it is getting minimized, and that is how we computed here. W equal to 2 and b equal to -7, the loss value is 0, okay. These are all the loss values which are plotted here and as a 2-dimensional graph. I hope you understand this picture. So this picture shows the loss value which is getting minimized, all right. Loss plot, otherwise we see. Fine. Now, how to find this loss plot mathematically? We are interested in that. Okay, we are going to see that. Right. Now, to calculate this, I already told about something called as this delta W and delta B, right? So what is this delta W? What is this delta B? We are interested to find this. I mean, manually we can find this actually, I mean, with human computation, but it is very hard, right? But mathematically, how a machine is going to understand this, how it's going to compute that, we are interested in, okay? So we're going to do that process here. You can see, instead of guessing delta W and delta B, we need a uniform way to change W and B based on the loss function, okay? Now, let us formulate this more mathematically. How does it work? Now, we'll just take theta as this W and B, okay? Because the important factor, parameter to involve is W and B. Based on W and B only, we are going to find the loss, right? So we just take it as theta, which is having these 2 points, the scalars W and B. We just collect it as a vector here, okay? Array of vector, fine. It's a 1-dimensional vector, where theta is a vector containing the values of W and B. Okay, now we are going to find the difference of that, which is delta theta, which is delta W and delta B. This is a parameter we are interested in to increment this W and B. Understand? As we already know that, right? But delta theta is the change in vector as W and B changes. All right. Now we are going to find this theta, where theta is nothing but theta plus eta into delta theta. What is this? I will tell about this with this picture. You will try to understand now. So as I told you, there are a lot of losses here, right? Definitely the new loss should be lesser than the old loss. Then only we will get the, even though there is a fluctuation, finally at one level, the loss which you are going to arrive at, definitely it should be lesser than the previous loss. That is what our calculation is. That is what we are going, that is a catch here, okay? We are going to, we are interested to compute that, right? So now how does it work? It's like you have the vector theta here, okay? We all know the vector is, it is having the magnitude and the direction. You have this vector theta. Now we have a difference vector, which is delta theta. You see this line, this is delta theta. You have the difference, okay? Now, when you add this theta with the delta theta, by parallelogram law of vectors, you get a new vector, theta nu, which is between this theta and delta theta, okay? So the sum of this theta and delta theta, let us forget about eta now, okay? We'll just take only theta and delta theta, we just add, okay? Theta plus delta theta, this is a new, this is a vector, this is a vector, we're going to add that, and we're going to get a new vector, theta nu, okay? This theta nu is exactly the diagonal, okay, of this theta and delta theta. But now you can see this theta nu is having a larger distance, a far distance from theta, okay? It is having a huge distance. So we are not going for a more fluctuation. For that, we are going to introduce another parameter which is called as eta. This eta is very, very, very small, okay? Like 0.001 or 0.0001 like that. So that when you multiply with the delta theta, okay, what it does is we are going to see, you know, this delta theta is a directional vector. We are not going to travel more, okay? We are just going to just take few steps and stop up to this, okay? We just restrict our direction so that the new, this theta and eta into delta theta, it gets added up and it is going to leave a new theta nu in the red line you can see, okay? Which is very closer to theta. Why I am skipping this diagonal is it has got larger difference. I don't want to have a larger difference. I want to have a very smaller difference between theta nu and theta. Understand? So that is why I'm just restricting this delta theta in direction which we just walk few words and stop, okay, because it's a direction, right? It's a vector. We all know vector is a it's a magnitude and direction. Of course, this direction is restricted for delta theta, and we are going to have eta. So now we'll talk about eta. Eta is nothing but some learning rate for this delta theta, how much it should travel, okay? So eta may be, as I told you, it is very negligible. We have to multiply with that and we have to add this. And that is how you get this theta plus eta into delta theta, where eta is a learning rate and which can accept a very negligible change in the theta, all right? So now we're interested to compute this delta theta, where this delta theta is going to show the loss of theta nu is going to be lesser than the loss of theta old, okay? This is what we're interested in. So this is more, let us dive into more mathematical concept, okay? So even if you're not understanding this concept, we can be a ML practitioner or a DL practitioner. It doesn't matter with a Python code, but still we are today as a webinar talk, we are interested in learning about the mathematical perspective. So I'm talking about it, okay? So we'll go for it. So we are going to compute this concept delta W and delta V by using the principles of Taylor series, okay? So why Taylor series is useful, let me tell about that. You can see here our objective is to show that we are going to change, I'm just taking only W so far, okay? Then the same principle holds for B also, okay? Just because theta has got both W and B, right? We're going to change both, of course, right? We are going to increment. So I'm just going to talk about W alone. So W get incremented with eta into delta W. You know what is delta W? It is delta, which is nothing but it is coming from delta theta, okay? So it is a scalar actually, because delta theta has got delta W and delta B. These are all scalars. W is a scalar, okay? So now we're going to find the loss of W, and we are going to find loss of W plus eta into delta W. Definitely this one should be lesser than this one. That means in other way you think loss of this one should be lesser than the loss of the previous one, okay? Fine. Now we all know what is Taylor series. Taylor series is f of x plus delta x equal to f of x plus f dash of x, the first derivative of f with respect to x by 1 factorial in delta x plus second derivative into by 2 factorial into delta x square and so on, okay? Now we are just taking this Taylor series and we are going to compare this Taylor series with our loss function. Now we are going to convert this f of x plus delta x as loss of W plus eta into delta W, and f of x is loss of W, okay? We are going to do that, and of course we are going to change this, okay? This derivatives, we call it as gradient here, okay? We are going to use the notation called del here, okay? Not delta. Del will be giving you the direction, I mean the derivative, okay? Of course the directional derivative, because we are going to use the vectorized Taylor series here, because this is for scalar, okay? Now we're going to plot it for the vector. Now this is for W, the same holds for B also. Suppose you just want to plot it for B, you're going to take B equal to B plus eta into delta B. B is approaching that, then loss of B will be greater than loss of B plus eta into delta B, okay? Same for B. So I'm not telling about that here, okay? We'll go for the next slide. So now we're going to have the more intuition over this Taylor series. The ultimate aim is to deduce the parameters as follows. You can see eta to be converted as eta plus, W to be converted as W plus eta into delta W, B to be converted as beta plus eta into delta B. So this is the increment we need, okay, for algorithm to work out, right? Now we are interested in finding what is loss of W and what is loss of B, and we are interested in finding the increments loss also, like loss of W plus eta into delta W and loss of B plus eta into delta B. Now, obviously, we are interested to say whether these losses of the new increments should be lesser than the old loss, of course, okay? And that means the loss of new increments should be lesser than loss of the old increment, okay? So loss of old parameters of W and B, okay? Fine. Now, as we know, what is this W and B? This is nothing but theta. As we told, theta is W and B. Now, this loss of theta plus eta into delta theta should be lesser than the old loss, okay? Mathematically speaking, we are having this kind of structure. Now, this is nothing but the vector. As we know, theta has got two scalars, W and B, which is an array of scalars which is fit into a vector, okay, one-dimensional vector here. Now we have loss of theta plus eta into delta theta. Now you just compare this. You see f of x plus delta x, which can be taken as L of eta plus delta theta into delta theta. This is for W. Same way for B. When you add it up, you are getting eta, because eta has got both W and B. Okay, you're getting theta plus eta into delta theta, which is equal to L of theta. Instead of f of x, we have L of theta here, plus this derivatives. Okay, this derivatives, we are going to use this one. this is eta, right? Eta is there. U transpose is nothing but your delta theta, which has got delta W and delta V, okay, multiplied with the gradient of L, okay. The gradient of L is nothing but your loss function, which has got W and V. I will tell about what is gradient. We are going to compute that, okay. This is the substitution for f dash of x into delta x, okay. We are substituting for this place by 1 factorial is mixing here. Of course, 1 factorial is 1, and here it is 2 factorial. You have eta square into the same thing into u will be there, okay. Like that it goes on. So this is how we fit in the vectorized Taylor series, right? Now, for convenience, what we're going to do is we're going to take this u as delta theta, okay. We are going to substitute this delta theta as u here, so that the equation or the expression gets minimized, okay. We will have a good form. L of eta plus theta plus eta into u will be L of eta theta plus this one will be same, okay. You get in this form. All right. So now I just change this delta theta as u. That's what I have done. It is something like looking like delta x, okay. Here it is nothing but eta u here. Fine. So now eta is very, very small. For example, eta may be 0.001. It's a learning rate. So we do not mind about that, okay. We are going to bother about this new loss, which is going to be lesser than the old loss. That is our way of understanding. All right. Fine. Now you can see this eta square, eta cube in this vectorized Taylor series. These are all actually, if you substitute eta as 0.001, then eta square will be very, very lesser than eta. Yes or no? Because it will be, into 10 to the power minus 6, of course, eta square. This one will go very, very smaller. So if it's very, very smaller, we can avoid all these points, okay? Except we consider only for eta. Let us take only this first term along with L of theta. We will just try to eliminate eta square, eta cube, etc. Why? Because it is going to give you a very, very, very small value, okay? So that is how we have, so eta square, eta cube, etc. all end up very negligible, and hence we could remove these corresponding points, okay? Now the new vectorized Taylor series will be L of eta plus theta plus eta u is approximately equal to, we are not saying equal to because we have excluded these points, okay? I mean eta square and eta cube and all. So we keep only these two, okay? And we are just trying to formulate it. L of theta plus eta into u transpose del with respect to theta into L of theta. Now what is this del with respect to theta? It refers to the gradient with respect to theta, and it consists of the partial derivatives of L of theta. You know what is L of theta, okay? It is with respect to W and B, okay? Stack. This is the loss function with respect to W and B, and we are going to take the partial derivative for that, and we are going to find the answer, right? Now, totally speaking, we have this L of theta plus eta u. This is going to be a real number, okay? Because it has got, any value when we want to find this loss function. All the loss function values are, you have seen this loss function. What are these loss functions? They are all real numbers, right? So obviously this loss function will be a real number, and this L of theta will also be a real number, okay? So these two are real number, and whenever these two are real numbers, obviously, and eta, of course, it is very negligible quantity. It is 0.0001, something like that. And what about this one? Of course, this should be a real number. Why? Because when you add two real numbers, you're going to get a number. Otherwise, it is meaningless. This L of theta plus eta u will never become a real number here, okay? So we need to have an intuition that this is going to be a real number, of course, right? So how it is going to be a real number? It's very simple, because u has got, what is in u is delta theta. What it has got, delta theta has got delta w and delta v, right? This u, which is in the transpose form, that means in the row form, for example. Now this vector, it is nothing but delta with respect to theta with L. This is nothing but the partial derivatives, because L has got, w and v. Now we are going to find the derivative of w and v. So whenever you have two parameters, then the partial derivative is going to get applied, because you have two parameters there. Then you have dou L by dou W, dou L by dou V. That is what we compute here, okay? So when you have this, when you multiply this values, okay, here this is a value we have here, okay? When you multiply that with this U transpose, again you are going to get a scalar here, okay? So this is going to be a scalar, and this scalar is going to be in the real number system. Of course, it belongs to R2, okay, not R simply. Exactly speaking, it belongs to R2, which has got 2 points, right? So all are having the real numbers, and when you add, you're going to get the real number here. Fine. So this is how we work on. So this part is U transpose into del of theta with respect to theta, and to L of theta is the dot product between delta theta. That means this U is nothing but delta theta, right? You are going to take delta theta transpose and the partial derivatives of delta theta with respect to a loss function, which is a real number. Okay, this is how we interpret this model. Now you see from the Taylor series we got only this expansion. Now what I'm going to do is I'm going to take this L of theta to other side so that it will become negative, right? L of theta plus eta u minus L of theta, which will give only this. That is going to be the next step. Now how to compute this? You see, we just take L of theta plus theta plus theta u equal to this one. We're going to rearrange this. We're going to take this L of theta to the other side, and we're going to get this equation. All right. So this equation now, our aim. What is our aim? Our aim is to minimize the loss function. That means this is the new loss function. This is the old loss function. We are going to say this new loss function is going to be lesser than the old loss function. Okay. How to say that? We are going to show that this difference should be a negative number. That means it should be lesser than 0. When it's going to be lesser than 0, what will happen? This one will be lesser than L of theta. I mean, L of theta plus eta u will be lesser than L of theta when you have this number to be negative. Now we are going to make this negative. How we are going to make this negative? We will just try to understand it. Note that the move eta into u would only be favorable if this one is 0. What I said has been dealt here. So this should be lesser than 0. This part should be lesser than 0, so that the new loss will be lesser than the old loss. Okay, because when you take this to other side, in this 0 side, it becomes L of theta, and L of new loss will be lesser than L of old loss. That is the objective for the loss function to be getting minimized here. All right. Now this one should be inferred as lesser than 0. How to infer that we will understand. So to make this, of course, eta is very negligible. We're not concerned about that. But what about u transpose into delta theta of L of theta? That one we are going to make it as less than 0. How to make this less than 0? We are going to do it using the angle function. Okay, already I told you, like this is going to, u transpose is going to be a vector because delta theta is a vector, and del of theta with respect to loss function w and b is also vector. There are two vectors. Okay, and I mean, before getting dot product, it is a vector. Understand? This u transpose is a vector. Del of theta with respect to L of theta is a vector. When you take dot product, it becomes scalar. Okay. Now, before that, it is a vector. Now, we're going to find this angle between this u transpose or u and between these two, right? So, let beta be the angle between u and delta theta of L of theta. Okay, this L of theta is having this delta theta of L of theta. So, we are going to find this. So, how to compute this, we will see here. I'm sorry, this is del. Okay, wrongly mentioned. All right, I will just correct and send you. Fine. Now, here you see this. Computation, what I'm going to do now, the angle between two vectors is given by cos theta. Okay, the rule, it's cos theta is equal to dot product of the vector divided by the magnitude of that vector. That is the rule, right? So we're going to take beta as the angle between this u1 delta theta into L of theta. Okay, so now we're going to find cos beta equal to u transpose into del of theta divided by magnitude of that. Okay, we are going to find the magnitude or the norm of this two. Okay, this is going to be a magnitude, right? Now this is cos beta, and the cos function ranges from -1 to +1, as we all know. So cos can take extreme value to be negative, which is -1, and the positive value to be 1. Of course, it is a range. All right. Now this one, norm u into norm delta theta of L of theta. Again, this is a error here. It should be del. Okay, I'm sorry. I will just correct it and send you. Okay, due to some LaTeX error, it is actually just del only. Okay, del theta. So now this del of theta into L of theta, del of theta and L of theta. This term should be, we will just make it as k. Okay, this value we will make it as k. Now we just consider this k. Now we will have to multiply this with -1 and +1, as we all know, right? We will multiply this with -1. It becomes -k less than or equal to u transpose into del of theta into L of theta less than or equal to k. I'm sorry, this one, this small delta and all, it's nothing but your del actually. Okay, I will just correct it and send it. Don't mind about this terminology. I mean, sorry, this notation, it is wrong actually. This is all this or nothing but del. Okay, del. I'll just correct and send you, right? So this is your k. Okay, we are going to multiply this with -1 and +1. So how now our values -k less than or equal to u transpose into del of theta with respect to L of theta in less than or equal to k. This is our expression. Now, what is our aim? We need to find this value should be reaching to a negative number. Why it should be negative? It should be most negative, so that our loss function will be, this value should be most negative. How much it should be most negative? Up to -1. Understand? The maximum negative number, okay, it can reach here in cos function will be -1. Okay, So this should be equal to -1, so that it reaches the maximum negative, so that our function L of theta plus eta into u minus L of theta will be lesser than 0. Understand? So we need to compute this k, which should be -1. We just compare with this cos beta here and -1. Cos beta should be, the extreme value should be -1. That means this value should be -1. We need to find -1. So when this cos beta will be -1, whenever beta should be 180 degree. Okay. So whenever beta is 180 degree, cos beta will become -1. So for beta, the angle to be 180 degree, then this function u transpose into del theta of L of theta will be -1. When it is going to be the extreme value, negative value, then this number will be lesser than 0. That is the most extreme value. Then you substitute that, then this loss function will be getting minimized. I mean, the new loss will be minimized to the old loss. Of course, it is getting decremented, right? So this is our aim. So here to infer that, you can see L of theta plus theta u minus L of theta equal to u transpose to del of theta, which is nothing but k into this cos beta term. You know, this k is nothing but -1, which will be most negative when cos beta is equal to -1. Understand? All right. So now this -1 quantity, how it arrives, this is the most negative value of cos whenever beta is 180 degree. Okay, and k value will be any number. When you want to multiply that with a negative number -1, it becomes negative, because we are talking about this k, and for what values of cos you are getting 180 degree for -1. That's why we are multiplying that with -1. Okay, that is how you compute this answer. And now you got this. Right, now the gradient descent rule. Now how it is going to work out is, the direction u that we intend to move in should be at 180 degree with respect to the gradient. In other words, move in a direction opposite to the gradient. Okay, so I'm getting some disturbance actually with the audio. So the coordinators, can you please try to convey this to the participants who are in the audio? Please try to mute themselves. Right. So I'll just continue. So you have this this gradient. When we talk about cos function, for example, there is a function cos here. We are going to just try to go in opposite direction so that you're getting this negative number. Okay, so that is how it is interpreted here. Okay, the direction u that we intend to move in should be at 180 degree with respect to the gradient. In other words, you move in a direction opposite to the gradient. Okay, when we move in a direction opposite to the gradient, then we are getting this -1, which is 180 degree exactly. Okay, right. So by this it becomes lesser than 0. All right. Now the parameter update rule, what it's getting updated. Previously, what it was actually, it was w plus eta into delta w, b plus eta into delta b. Now this quantity become negative, right? So what it infers here is it will be wt plus 1. The new white should be the old white. This plus term changes to negative because of we are interested in making this delta w into eta to be a negative term because of this cos directional behavior with the vector with its increment. Okay, we are going to find the angle, and hence we are interested to compute this. We are getting a negative answer here. That's why minus comes into the picture here. Okay, so this is a parameter update rule. We have this wt minus eta into delta wt, and bt plus 1 equal to bt minus eta into delta bt. This is a new method, because based on this only the algorithm works out in emission. Okay, so it is going to, I will just formulate this in the final complete learning algorithm at the last slide. All right. Now, what is this delta wt and delta bt? It is nothing but the partial derivative with respect to w and the partial derivative with respect to b, because you have w and b, right? So whenever we want to take the partial derivative, then you're interested in finding a derivative with respect to w. So we are using partial derivative, and we are interested in find derivative with respect to b. So you're using partial derivative. So we have dou L by dou W and dou L by dou B, which are nothing but your delta values of W and B. So this is our very important step. We are going to compute mathematically. Okay, how we are going to compute, we will see by some example. Right now, this is the complete algorithm. Okay, so before getting into the final touch, we will just try to understand what this algorithm is like. The algorithm is now we are initializing W and B randomly. Now we are going to iterate over data. First, whenever we pass this to a machine, okay, this is the algorithm we are going to pass to the machine. So it computes the y hat, okay, the new predicted output. Now, based on the old output and the new output, it finds the loss function, okay, L. Then based on this loss function, it's going to find wt plus 1 and bt plus 1, okay, by using these rules. Okay, we are going to find all dou L and all those things, partial derivatives, and we are going to compute this wt plus 1, bt plus 1. And based on this, okay, we are going to finalize the loss function, whether it is going to be minimum or not. Again, we are, based on this w and b, whether our output is going to be very closer to the original output or not, we are going to check. If not, we are going to iterate it more. We are going to iterate again and again, and we are going to find the new w's and b's, and based on that, we are going to find this loss function again and again, and we are going to give, make the algorithm more efficient. This is our objective actually. Okay. Now this could be approached, this dou L by dou W, like we get this delta W and delta B. This could be found using a PyTorch or TensorFlow with one-line function. Directly you can code it and you can find this answer. It's very easy to find within a second a machine does, but how mathematically it is working out, we are interested in. Okay. Now when it is getting satisfied, okay, this algorithm will be satisfied whenever the number of epochs, that means the number of iterations of the passes, may be more large, maybe 1,000 passes or more than that, or whenever the loss is going to be very negligible, like epsilon, the loss will be lesser than epsilon, we can continue till that, or whenever the loss function will be just passed with only few iterations. For example, 100 iterations, we can just pass it up and we can just make this, sometimes it may lead to some overshot of the results with the plotting points with the sigmoid curve. To avoid overshot, we can just make it with some, passes, maybe some 100 passes like that. We take that loss and we finalize that new loss so that it is enough for us to understand the model is going to get fit with the sigmoid function. Understand? So this is our complete learning algorithm. Now, the last slide, which is going to tell about what is delta W and delta B. How do we want to find this mathematically? We're going to do that. Okay, we're going to see that here. So let us find this computing. We have to compute this partial derivatives, delta W and delta B. To compute this, so we just take, you will just consider the loss. For example, you just take, this is the loss function. As we know, this f of x nothing but your function which you are going to find. This is the predicted y hat. Okay, this is your y. Now for 5 values, I'm going to find the loss function. This is the loss function. We are going to take the difference, square it up, sum it up, and take the average of that. This is the loss function. Just for 5 points I took. Okay. Now, what is delta W? I'm interested in finding what is delta W. What will be delta W? It is nothing but dou L by dou W. And we can find delta B also. We are going to find that. Okay. How to find this? See, you just take the partial derivative of L with respect to W on both the sides. So I take dou by dou W of this term. Now I'm going a little bit in depth into mathematics here. Okay, you can understand the partial differentiation, what it does here. Okay, it's a high school mathematics, not a big level. You can understand it very well. All right. Now this is delta. This is capital delta W. We have this. Okay. Now we are going to take, how many points are there here? We have 5 points, of course. We're going to take 1 point. Okay. We will take only dou by dou W of f of x minus y whole square. Only 1 point I am interested in. From this points, 5 points, I will take only 1 point. Dou by dou W of f of x minus y whole square. Right. Now this is our del. Del is nothing but the gradient, which is nothing but the partial derivative of L with respect to W. Okay. That is the way to understand. Now, how to find this answer? Everybody can understand. Those who know mathematics, definitely you can understand it better. Like you're going to find the partial derivative of this function with respect to W. Now, can you tell me what is this f of x? This f of x is nothing but the sigmoid function. This, see, I'm just keeping my hand here. You can see 1 by 1 plus e power minus wx plus b, which is having W as a function. So this is f of x is having the parameter or the variable W. So definitely it is differentiable with respect to W, right? But what about y? Y is a scalar, okay, and y does not have any, it's a constant. So when you differentiate y with respect to W, it becomes 0, right? Now how to compute this? We just differentiate, the differentiation of this one will be 2 into f of x minus y, which we have done. Now you don't worry about this 1 by 2. This 1 by 2 is added extra to make our machine learning algorithm work efficiently, of course, okay? So if you don't want this, you can exclude this also, but to cancel out this W, we are trying to add this 1 by 2. If not added also, it doesn't matter. It doesn't matter much, okay? So do not worry about that, okay? Just keep this 1 by 2 as it is and you try to partially differentiate this. Now you take 2 times f of x minus y. Now we are gonna, this is function of function rule, as we know, right? 2 times f of x minus y. Now into dou by dou W of f of x minus y. Now you are gonna differentiate this, right? Now, when you want to differentiate this y differentiation becomes 0, as we know, right? I mean, dou by dou W of y is 0. But what is dou by dou W of f of x? That is nothing but dou by dou w of 1 by 1 plus e power minus wx plus b. Okay, I hope you understand these steps. Okay, this is not a big mathematics, high school mathematics. You can understand it better. Like it's a small partial derivative. Up to this step, I think this is clear, right? The flow, fine. Now we are interested in finding. We did not stop the story here. We're gonna build it up. We're gonna find the final answer. Let us see how it works out. Now I'm gonna find only this dou by dou w of 1 by 1 plus e power minus wx plus b. That one I calculated. You can see here dou by dou w of 1 by 1 plus e power minus wx plus b. It's nothing but you just think this has some p, okay? Some variable p. Now it is like 1 by p, right? Now what is dou by dou w of 1 by p? You know how to differentiate this, right? So it is again a function of function rule. First you differentiate this, again you differentiate that with respect to w, right? So now I'm going to differentiate 1 by p. For example, you consider this as 1 by p, okay? 1 plus 1 e power minus wx plus b. So 1 by p differentiation is minus 1 by p square. That is this term into dou by dou w of this quantity. You know how to differentiate this. Dou by dou w of 1 is 0, of course, plus dou by dou w of, because the derivative sum is equal to sum of the derivative, as you know that, right? So it is dou by dou w of e power minus wx plus b. How to differentiate this one? We just take e power minus wx plus b as e power same, okay? Because e power minus x differentiation is e power minus x into differentiation of this term with respect to b, w, because you have w also, right? So it is nothing but minus of wx plus b. We are going to differentiate this dou by dou w of this term. Understand? So that is how we are going to work out here. All right. So now when you do this process, what happens? I mean, I'm talking only about dou by dou w of e power minus x. Understand? So we're going to differentiate this. Now this one gets differentiated. It's 1 minus 1 by this term square. Everybody knows this well, I hope. This is the same term, e power minus wx plus b into this term differentiation is minus w. Okay, you are sorry, minus wx differentiation is w. You know this is x is a constant with respect to w, so you have minus x here. Okay, plus b is a constant, therefore it is 0, so you have minus x here. Okay, you are differentiating dou by dou w of minus wx, which is minus x. Understand? So this is how we arrive at the result. Now we have this function minus 1 by 1 plus e power minus wx plus b whole square into e power minus wx plus b into minus x. Now here you have power 2, right? Now you split this minus 1 by 1 plus e power minus wx plus b into 1 by 1 plus e power minus wx plus b here with e power minus wx plus b, okay, separately into minus x. Now why I do like this? Because you have, you know, this one, again you multiply minus into minus becomes plus, okay, minus 1 into minus x. So avoid this negative. This 1 by 1 plus e power minus wx plus b is nothing but your function f of x. Now this one, e power minus wx plus b by 1 plus e power minus wx plus b is nothing but, we just add and subtract 1 here, 1 plus minus this term. So one term will be 1, okay, because when you cancel this, you'll get 1 minus this term you'll get, that is where f of x. So I'll just leave this computation to yourself. One who is interested to do that, you can do that and see. It is 1 minus f of x. You will arrive at 1 minus f of x into x of course, okay, because this minus and minus getting multiplied to get positive. So the final output for this this term alone, dou by dou x of 1 by 1 plus e power minus x b will be f of x into 1 minus f of x into x. Okay, this term we're going to take this and we're going to put it where? Here in this place. Already, what is del w? It is f of x minus y into this quantity will be f of x into 1 minus f of x into x. Okay, that's what we are just substituting. Now we obtain your del our del w to be f of x minus y into f of x into 1 minus f of x into x. All right. So this is for one term. Okay, this is for one term. Now we are interested in finding for 5 terms. For example, this is only one term. This del w, I'm going to substitute it in this function. Okay, for one term. So for 5 terms, what will happen? You can see here, 5 terms you are getting. You just add this. Okay. So when you just add it, you just sum it up and multiply with 1 by 5. Okay. So for 5 terms, you will have f of xi minus yi into f of xi into 1 minus f of xi into xi. Okay, where I runs from 1 to 5. This is for delta w. Similar way, we can also find delta b. Okay, we can find delta w as well as delta b. Okay, so these two are the main concepts which we are concerned today in mathematical understanding. We approach these answers finally. Now, based on this answers only, how our system will compute this one, you know, f of xi, it will take our original sigmoid function, and y is the training data, and again f of xi into 1 minus this sigmoid function into xi. It will compute that for each and every I term in a for loop. It will compute, and we can make a class function by ourselves in Python so that we can just work on it and we can sum it up and find this answer. Okay. So this programming part, I will leave it to you. I'm not going to use any programs today. Just I'm handling only the mathematical part, which we are interested in today. All right. So we obtained this delta W and delta B. So this is what we are interested in to find this parameter delta W and this delta B. We are going to find it with the angle as a negative parameter. Okay. So once you find this, and the system will find that, and it will put it here, and it will increase the weights and the bias, and again it will compute. Okay. This process, it goes on until we get the loss function to be minimized. Okay. Once the loss function is getting minimized, it will stop the algorithm. All right. So this is how it works on. So I hope you understand this concepts. Okay. This is the loss function computation, and this is giving the complete algorithm structure here. So this is the concept for today. Today I just took an algorithm, I mean the sigmoid neural function, and I just thought of making you understand about the loss function, how it gets minimized by using the mathematical techniques. Okay. So these are some mathematical ideas behind the algorithm. Okay. Fine. So that's it for the presentation today. And at this moment, I would like to thank the professors, Dr. Mitesh and Pratyush from IIT Madras, who has provided insight of finding all these mathematical ideas, who has given an exposure in the other side of the coin, how it works in mathematics. Okay, the algorithm works. So hats off to them, of course. Okay, so and this I did not put any reference. I'm sorry. This actually all these references parts available in the net. Okay, in the website, and you can you have some blogs. Okay, written by some data scientists like Niranjan. Okay, they have done a lot of mathematical stuffs. Okay, they just put in their blog spots. You can find it very interesting. One who wants to take this deep learning and proceed their career, they can understand these concepts if you are very much interested in mathematics, so that you can try to make your own algorithm, of course, and try to build it by yourself in deep learning. Okay, so that is for today's presentation. Thank you so much. I will stop this with this, and I hope you understood it better. Maybe I am a little fast today, but still, I will just provide this PPT to you. You can just understand it and try to get the basic concepts, of course. Okay. So thank you all.
Thank you
over
so
to the
much.
host. Thank you so much.
Thank you so much, sir, for your wonderful explanation and presentation on deep learning in mathematical perspective. We are enlightened with your knowledge. In particular, your explanation on sigmoid loss function, sigmoid neuron, and complete learning algorithm is extraordinary. There is a question in the chat box. Participant Mr. Rahul Pandey asked, sir, it is very long algorithm, so can we make a computer programming so that it's reduced our complexity computation?
Yeah, of course, yes. As I told you, we can just make it as a program. That's what I have given this algorithm. Who was asked this question? That's what I have given this algorithm, right? So this algorithm, it's a pseudocode for a program. You can make it as a Python program. We can define our own class for all. Okay, you can find the loss function. We can define a class for it. We can define the class for finding this constants W and B, these parameters, and we can just try to find a class which is going to get minimized with a loss function, and we can get the answers. Okay, we can just frame it as a program. Definitely, to frame as a program only, we need all these concepts. Of course, I'm just talking about the behind the screen what is happening actually in mathematical way. Okay, of course, in one line code in PyTorch and TensorFlow, you are used to, I mean, directly get the answer. Okay, already these are inbuilt packages which is coming along with Python, so you can understand it very well. You can just take from Python, and you can just in a second you can find this answer. Not much, right?
Okay, sir. There is one more question from Mr. Chandran. Sir, as a mathematician, can I do PhD in deep learning? If it is, where?
Yeah, of course, very well. You can do a PhD in deep learning, of course. No doubts about it, because nowadays you have got a degree certification for machine learning and deep learning. You can be as a data scientist. Okay, for the next 5 years, artificial intelligence is going to rule out the world, and machine learning and deep learning is going to definitely, but I mean, definitely make the human work getting less. Make it less, so that it rules or conquers the world, of course. So definitely you can make a certification over deep learning, and you can pursue with your research with the deep learning techniques, and can definitely be a successful data scientist. Yeah.
Thank you so much, sir, for your crystal clear explanation. And you have
thank you so
answered
much.
all the questions patiently asked by the participants. Now I invite Mr.
Thank
G.
you.
Balaraman, Assistant Professor, Department of Mathematics, St. Joseph Institute of Technology, to deliver vote of thanks.
Yeah.
Thank you, Satish sir. Good afternoon. I consider the occasion as an honor and privilege to extend the vote of thanks on this day. On behalf of Department of Mathematics, wholeheartedly convey our gratitude to Dr. B. Babu Munagaran sir, Chairman of St. Joseph Group of Institutions, for his enormous support to organize this webinar.